Welcome back all of you. Before starting today's lecture, let us have a brief recap on what we did last time. In the last lecture, we had introduced the concept of exposure as the regression coefficient. We have a risk factor and we have a account which may be an asset, a liability or an operating income which is influenced by that risk factor. Then the sensitivity of that account, value of that account to the risk factor determines the exposure of the firm, of the entity. We also defined risk as a measure of the variability of the exposure in consequence to the variation in the risk factor. To make it more precise, we look at the regression equation. We have it on the slide. Y(i) is any particular observation consequent to an observation xi, and that consists, as I mentioned last time, that consists of two parts. We have segregated it in two parts. One part is the systematic component, the component that varies in tandem with the variation in x, and the other part which may be due to other factors which we are not either able to enumerate or which are arising due to measurement errors, or they are factors the evolution of which we do not know. In any case, we are more concerned, the predominance of the variation is captured by the factor x, and therefore we model the rest of the variation in terms of a random variable which we call ai, and then ai is split up into its mean value, that is alpha, and the variation about the mean value, that is ei. So, we have the expression yi is equal to beta. Beta is the sensitivity, beta is the exposure, beta of xi plus alpha, which is the mean of the random errors, and the variation of each value about the mean, which is ei. Obviously, then the sum of the ei should equal 0, because they are variation about the mean position. We also require that the covariance between xi and yi must vanish, that means this must be equal to 0. The regression equation, that is the equation of the straight line f g, which is obtained by ordinary least squares regression, is the line that best fits the set of data. The set of data points, for each data point, for each I we have a data point in this diagram, and the set of data points that are best fitted by this straight line are given by the expression y is equal to beta x plus alpha. Alpha is the intercept and beta is the slope of the regression line. And this also indicates a systematic or a predictable relationship on the average, not for every value, but on the average a predictable relationship between y and x, which is captured by beta. As I mentioned last time, the process of optimizing or the process of minimizing the squares of the deviations, that the squares of E, the sum of the squares of E, that is why we call it ordinary least squares regression. The sum of the squares of E, we minimize that. The process of minimizing of this squares gives us the value of alpha and beta, which are given on this slide. This is the value of beta and the value of alpha is given here. This is alpha, this is beta. I have reworked out this optimization without using matrices for the convenience of some of the viewers who may not be accustomed or who may not be familiar with the use of matrices. Therefore, I have retained both the slides, the previous slide as well as the slide which does not use the matrices. You see, now the important thing is, as an input, that the covariance between ei and xi is 0. Therefore, we are able to split the standard deviation or the variance. We are able to split the variance into two orthogonal parts. One is the part beta square, sigma square delta s, that is sigma square s in our case, this is a general case, and sigma of the error term, sigma square of the error term. This particular part constitutes the systematic risk beta square, sigma square, delta S, and this particular part constitutes the unsystematic risk. This is the random risk due to factors which we have modeled as a random process. The risk arising due to factors that we are not familiar with, but we model them as simply as a random variable, and this is the risk which arises because of the systematic relationship between x and y. The variation of x, the impact of this on the variation of y, the fluctuations in y due to the fluctuations in x are captured by this systematic risk term beta square, sigma square, delta S. The second term, again I reiterate, is the random term that captures the portion which is not arising due to the systematic relationship between x and y. Now, at this point I take a detour, I take a slight digression. I would like to discuss in detail the concept of randomness. We have been talking about randomness throughout. And we shall be talking about it throughout the entire course, in fact. Why? Because the prices of most of the financial assets evolve randomly, or that is what we perceive it to be. Now, to start with, I would like to quote Albert Einstein, who was a strong proponent of the view that the world evolves in a deterministic manner. He said that God does not play dice. So, let us first understand what is determinism. Determinism means that given the state of a system at any point in time, let us say t equal to 0, we can arbitrarily scale it at the initial point. We can precisely, exactly determine the state of the same system at any future point in time. If we can do that, then the underlying system is said to be deterministic. The process of doing that is a standard problem in physics. I will not elaborate that. Basically, we identify a complete set of variables, either it is position and velocity or position and momentum, and then we, using physical laws, we convert the time evolution of these variables into differential equations, determine the solutions to these differential equations using certain initial conditions in respect of the values of the variables at t equal to 0, and these give us, on integration, these give us the values of these variables at a later point in time. The important thing that for us is that the values of these variables can be, and therefore the state of the system can be completely determined at any future point in time. That is when the system is said to be deterministic. Einstein firmly believed, and in fact Laplace and other scientists prior to Einstein, other than the advocates of quantum mechanics, firmly believed that the world evolved in a deterministic manner. But then as quantum mechanics came along, the concept of determinism took a huge beating in the sense that quantum mechanics has a certain inbuilt indeterminacy. Rather than randomness, it's I think we should use the word indeterminacy built into it, as pointed out by Heisenberg. To understand the meaning of classical randomness, let us first talk about quantum randomness. The first thing that we must know is that quantum effects are perceptible or are pronounced at subatomic scales, at scales which are very, very small compared to compared to everyday life. The scales that we encounter in everyday life are well explained by Newtonian physics or by the physics, classical physics we call it. So, we do not really perceive the quantum effects in everyday life. However, at the subatomic scales, for example, the Hadron Collider LHC, we have certain quantum effects which become very pronounced. Now, the issue here is that when we make a measurement at that scale, for example, if we want to measure the position of an electron, how do we do it? We do it by bombarding it with a photon or a beam of light or a beam of high frequency light, that may be X-rays, gamma rays or whatever, but very high frequency beam of photons, and we analyze the scattered beam which hits the electron and comes back to us, and on that basis we are able to determine the position of the electron. Now, what happens is, as soon as that photon hits the electron, there is a transfer of energy and momentum between the two, and as a result of which the state of the electron changes. And therefore, if we want to determine precisely the position and momentum of the electron at the same instant of time, it is not possible, because of the interaction of the measuring apparatus, the measurement process with the object being measured. So, this is a kind of indeterminacy which is built into quantum mechanics. However, at classical levels, as I mentioned, these effects are not pronounced. At classical level, if we talk about randomness, it was perceived by Einstein as a lack of information, absence of information, ignorance. He used the word ignorance. If you are ignorant about certain things, that ignorance manifests itself as randomness. Let us take an example. The toss of a coin is widely accepted as a random process, in the sense that the outcome, the head or the tail, is unknown, is unpredictable. Let us extend this argument. Let us assume that by some mechanism, some means, we are able to ascertain precisely all the influences that affect the tossing of the coin or the trajectory of the coin and its fall back on the earth, including, for example, the angle of the flip and the torque that is imparted, the viscosity of the air, the gradient of the air that it encounters, and every other factor that has a role to play in the tossing and the falling back of the coin. Will it not be possible? And we also know how these factors are likely to impact this particular experiment, and they can be modeled by a suitable mathematical process. If all these things are possible, if all these things happen, will the toss still be unpredictable? That is a very big question. Proponents of determinism argue that in such a situation, given the initial condition, we can find out the final outcome of the toss experiment. That is what they feel, and therefore, extending this logic to complex objects, they feel that it is our lack of knowledge, lack of information about either the factors, the manifestation of those factors, the evolution equations, or whatever it is. It's our inadequacy of knowledge, incompleteness of knowledge, that results in the unpredictability of the outcome, and what we term as randomness. That is the argument of the proponents of determinism. The other school that says that the world evolves in a random manner are equally convinced that there is certain intrinsic randomness which we have accepted more or less universally exists at the quantum level, and that a perfectly precise measurement is not possible, and therefore, there would be some measurement error which also contributes to the randomness. That is the perception of the school, which argue that the world evolves in a random manner. And they also feel that it is the accumulation. There is something called the Ehrenfest theorem in quantum mechanics. The cumulative effect of various quantum fluctuations results in a trajectory which, as the mean value, evolves in a classical path, but it is essentially an aggregation of quantum phenomenon. That is the argument, and quantum phenomenon being random, the argument is that the randomness, the cumulative effect of randomness manifests itself as a perceptible determinism, but intrinsically the world is random. This issue is still yet to be settled. However, for our purposes, what we accept for the moment is that randomness does exist, and it is probably due to our incompleteness of knowledge about the system, as a result of which we are not able to model each and every influencing factor in its entirety, and therefore, we model it as a random process. There is a quote by Stephen Hawking on this, does God play dice? It was in 1999. It's there in the slide. I'd like the viewers to read through this, or maybe I could read through this. The classical view put forward by Laplace was that the future motion of particles was completely determined if one knew their positions and speeds at one time. This view had to be modified when Heisenberg put forward the uncertainty principle, which said that one could not know both the position and the speed accurately. But even this limited predictability disappeared when the effects of black holes were taken into account. The loss of particles and information down black holes meant that the particles that came out were random. Now, this is I may add that this at the moment is contentious, that the loss of information when particles fall into the black hole is questionable. It is still not settled once and for all. One could calculate probabilities, but one could not make any definite predictions. Thus, the future of the universe is not completely determined by the laws of science, and its present state, as Laplace thought, God still has a few tricks up his sleeve. Okay, now coming back to the concept of hedging, we have a risk factor which we modeled by x or delta s in the earlier slide. We have a risk factor and we have an account. This account may be an asset, this account may be a liability, this account may be operating incomes, but the bottom line is that this risk factor or the variation in the values of this risk factor are going to manifest themselves as variation in the values of the account, which is going to influence our financial position. That is the backdrop. And what we want to do is, we want to eliminate or at least minimize the impact of this risk factor on this account. That is the concept of hedging. We have a risk factor, we have an account. The risk factor's value is the account's value is influenced by the risk factor's value. As a result of which, if the risk factor value varies, the value of the account also varies. And therefore, because entities prefer certainty to uncertainty, a risk is not viewed favorable by entities, by business entities. We want to evolve optimal mechanisms for the management of risk. That is what we call hedging. So, how do we do the hedging? We take a position in certain other assets or certain other financial instruments, such that when this risk factor acts on the account, and as a result of it the value of this account changes, it simultaneously acts on the hedge also. The same risk factor acts on the hedge also, but it acts in an opposite manner, and therefore, the changes in values of the account and the hedging instrument tend to be out of phase or diametrically out of phase, and they tend to cancel each other, and we get a situation or a combination of the two, such that it is far less influenced by the variation in the risk factor. To repeat, we have a risk factor which the variation in which results in a variation in the value of our account. We create a new instrument, or we do an investment, or do whatever, we take a position in a new instrument, and by doing that position or by taking up that position, a combination is created such that the impact of the variation in the risk factor on the account and the hedging instrument operate in opposite directions and annul the effect of each other. The variations annul the effect of each other. That is what is called hedging. Now, when we talk about futures, a very important concept is the concept of basis. How do we define basis in the context of futures? Basis is defined as the difference between at a particular instant in time. Basis is obviously a function of time, it varies with time. At a particular point in time, a basis is given by the difference of the spot price and the futures price at that instant of time. Spot price minus futures price at the given instant in time. Now, because both spot prices and futures prices are stochastic processes, they evolve in time as random variables. Therefore, the basis also is a random variable which evolves in time, and it is also a stochastic process. In other words, basis need not be constant across time. In fact, it does vary, it does fluctuate from time to time, and it not only fluctuates, it fluctuates in an unpredictable manner, because the spot price and futures price are both unpredictable. Therefore, their difference also needs to be unpredictable. But there is a caveat. The caveat is that although basis does fluctuate, being the difference of two random variables into two stochastic processes, at the point of convergence, at the point of the maturity of the futures contract, at the point of maturity of the futures contract, at this point, the basis must approach 0, must converge to 0. What does it mean? It means that at the point of maturity of a futures contract, the spot price of the underlying on this date and the spot price of a futures contract that matures on this particular date must be the same. Why they must be the same? Arbitrage once again. So, this arbitrage is literally universal in finance. You find it literally in every price determination mechanisms, literally, not precisely. Now, why is it so? Suppose the spot price is higher than the futures price. What do? I buy the futures and I sell it in the spot market. Now, that futures contract entails delivery on the same day. Therefore, I will receive the asset on the same day and I will sell it in the spot market. And conversely, if the futures price is higher, I will buy the asset in the spot market and deliver it against a short futures position, because that short futures position is also going to mature on the same day. So, neither can exist permanently, and as a result the two prices, that is the futures. Now, please understand which futures price we are talking about. We are talking about F capital T. What is F capital T? F capital T is the price of the futures contract on the date of delivery itself. So, F capital T is being compared with S capital T, that is the spot price on the same day. Spot price on the date of maturity of the futures contract and the futures price on that same particular day must theoretically converge. Otherwise, arbitrage will take place, which will compress the difference until they converge at equilibrium. So, how does the futures hedge operate? Well, as we discussed earlier, the forward price move in tandem with the spot prices. We also discussed that there is a close nexus between forward prices and futures prices. Therefore, by and large or within marginal variations or deviations, the futures and spot prices should move in tandem. Therefore, if you have a portfolio which consists of certain assets, which consists of certain securities, and you are worried about the price of the securities falling, you take a futures position, you take a short futures position on similar assets. So, if the price falls in the spot market of these securities, as a result of which your holdings value, the portfolio value declines, because the securities prices have declined, and the futures market prices mirror the spot market prices, therefore, the futures prices of those securities should also decline. Now, here I emphasize that the correlation need not be 1, but there is some correlation, some significant correlation between spot prices and futures prices. So, if spot prices are declining, it is very likely that prices in the futures markets of same assets would be declining, or at least similar assets would be declining. Now, if this futures prices are declining and you have taken a short position in the futures, what happens? You tend to make profit. So, at the end of the day, the loss that you have made on the portfolio due to decline in spot prices would be compensated entirely, partly, or over or under compensated, we will come back to that, but would be compensated by your short position in the futures market, which has also shown a similar trend in prices. Here one important thing is that when we talk about a hedge, it is not absolutely essential, particularly a futures hedge. It is not the practice that the futures are to be held until maturity, let us call it capital N. This is today, and this is, let us say, capital T is the period which is my hedge period. I want to start my hedge at this point and I want to complete I want to lift my hedge at capital T. Now, it is not necessarily true or not necessarily the practice that T and N should coincide. In other words, obviously, N can be greater, N cannot be less than T, N won't be less than T, although I will come back to it. But the common practice is that I take a position in futures at T equal to 0 and I liquidate that position by closing out the futures position when I want to lift the hedge. And thereafter, the futures may not mature at T, they may be live, but I can still take a counter position and cancel my position in futures. Suppose I am short in this futures at T equal to 0 for as a hedge, I can take a long position at capital T and thereby close the position. Although the futures may continue to survive, continue to be live until capital N, they will continue to be traded. So, that is one thing, that is one point that I like to emphasize here. The second thing is probably usually missed out, but it is very interesting. We do have a mechanism by which we can transform a sum of money from one point in time to another point in time. For example, from an earlier point to a future point, we can do it by compounding in any form that we wish, and conversely, if we want to work out the present value or an earlier value of a later cash flow, we can again do it. So, while for analysis we normally accept the fact that the hedge, the lifting of the hedge, lifting of the futures position or closing out of the futures position would coincide with the point at which my exposure materializes. For example, if I want to make the payment in dollars, I would make it at capital T and I also lift the hedge at capital. That sounds logical, that is logical, but that is not absolutely necessary. Suppose I get a better price at an earlier date, or I feel that the futures could be carried, the futures position could be carried till a later date to make more profit. You can, but then it could be this could be the speculation element embedded in my futures position. Maybe we could exclude that on that argument that this amounts to speculation, but otherwise as an entirety you are not bound to lift the hedge at the same point at which you are taking the exposed position, or you are making the payment, or you are receiving the payment at, that is at capital T. We will continue from here after the break.